speaker is Ruth Wunderlich. She's from St. Edward's University and Austin Community College.
Hi, I'm Ruth Wunderlich. So in 2010, I did some research with school data. What I did was I had data from one high school, and I had about 12 identified mathematics teachers, and I tried to use the student scores on the state test to determine who was better teachers at growing their children and who were the worst teachers, which is something we're legislated to do, as probably many of you know. So there's lots of things I could discuss with you. These are the things I'm not going to talk about related to this. First of all, a teacher can only teach so many students in a year, and you can only analyze a small number of years for it to make any sense. And so you have a sample size issue when you do this. In fact, when I did it, the numbers of student records I had for each of my 12 teachers ranged from 142 to 316. That was the sample size. I don't need to tell you the relationship between variance in the data and sample size. There's the formula we all are very familiar with, but of course, just because your models are more complicated, that formula stays the same. There's variability in the data, and the way you can kind of think of it as noise, and the way you can get through the noise to see what else is in the data is to have large enough sample size and random size and so on. So that issue doesn't go away. I'm not also going to talk about missing data. It turns out that when I did this, about 50% of students who were in these teachers' courses during those years, there was not sufficient data to include them in the analysis, that they were only being judged on 50%. And of course, it wasn't evenly distributed among the teachers. Seniors never took a test, so they were all many of the AP courses had really small enrollment sizes for this problem. And I'm not going to talk about assignment of teachers to courses, which, as you know, it's good practice to assign teachers to courses, and it should be good practice according to your understanding of the characteristics of the teachers. And this is a huge confounding variable in trying to do this. That probably cannot be eliminated, in my view. So that's what I'm not going to talk about. These are the things I am going to discuss with you. I'm going to talk about how I built a model. It's a multi-level, multiple regression model, and I'm going to talk about something called the 11th grade effect, which figured into my concept of building this model. Mostly I'm going to talk about this because this is the first time I've been in front of an audience that would actually understand this part of what I did, so I'm really excited to be able to talk about it. And then at the end, I'm just going to talk about another feature of the data that I did not recognize when I was doing the research, but recognized after the fact. And certainly, if I do more research, which I hope to do, I hope to have new data next summer, I'll certainly be working this feature into my model. It's probably a feature that's present in all of your state tests, and something that you might be interested in knowing about that, about the test data and how it behaves. You hear all the time when you read literature on doing this, on these growth models, value-added models, that students are not assigned randomly to classes. And one of the reasons you hear that all the time, and you don't hear the other thing that I said I wasn't going to talk about teachers not being assigned randomly to courses. The reason you hear this all the time is because there's actually a statistical way to manage that. So there's something you can do about it, unlike the other. So what you can do is do a multi-level model. So that means that you structure your data to match the way the data is structured. What I did when I did this is I did a first level of students and a second level of classrooms. You could argue that I should have done students and courses and classrooms to more accurately reflect the structure of the data, which is not what I did. But this is what I did. What you never see mentioned in the articles and the literature about this is that when you do that, of course, what you're doing is you're allowing your variability to have variability. And so, of course, that adds to that formula of the more variability, the bigger sample size, the harder it is to see the thing you're trying to see. And they never talk about that. They say, we have a way, we have a model that will work with this. if you might think that the way that these models work, from reading literature or even just thinking about it, is that you take your test score the student has had in the year after they've had a teacher, you subtract the test score they had the year before, and you get a different score, and then you do your analysis on that different score, which represents their growth. But that's not actually how these models are built. You think that if you, for instance, were from Texas like I am, for the last few years we've had something called the vertical scale score available to us, and we were told that's exactly how we were supposed to use it. And now we have a new test, and they haven't told us how we're going to measure growth with the new test, but they kind of imply that it's going to be these different scores. We're supposed to find out in the fall how we measure growth with this new test. But this is actually how these models are built. The regression, there's all the data. Those are all the student scores. That's over there in this tax, that's how they did the year after they had the teacher, and last tax is how they did on the test the year before they had the teacher, and there are all their scores, and of course, students who were doing poorly, and looks about like you'd expect it to look, and you can do a regression line, and this one has been done with the two levels that I described. Then the growth of the student is the residual, is that E term there. So all the students above that line are students who you would treat as having grown, having shown growth during the course of that year, and all the students below the line have shown a decline during the year. And so the way we're going to put teachers into this model, and it's a little dangerous to try and do a visual on these models as they get more and more complicated, but I think we can still do it here. Imagine that each teacher's students is regressed. And we assume that that slope there, that 0.7429, that's fixed for everyone. We all have that slope. But that then, because we have different students, we're going to end up at different levels, at different intercepts. And so that's what we're going to do. We're going to get each teacher to have their own intercepts. We're going to replace that gamma knot there with all 12 teachers, and each teacher will get their own gamma. And there it is. And so you see, you've got your 12 teachers down here, and each one has their own gamma. And then those numbers will allow you to rank the teachers. And the ones that have the higher ones, their students are showing more growth, and the ones that have the lower ones. So you might think that this is the model, and that there I've measured the teachers and I've measured growth. But that is not at all what I had intended, because I know something else about student growth, another variable that affects student growth in these test scores. It's what I like to call the 11th grade effect. I happen to know that in 11th grade, we call that the exit test. That's the test that counts for graduation. They're a little more mature. For whatever reason, the 11th graders show more growth consistently. In the aggregate, they show more growth always, ever. And so since I know that, I didn't expect this to measure students' growth. I actually expected this to measure very well the proportion of 11th graders each teacher had in their classes. And so this is where I skip a couple steps, go to the next slide. You'll see here that sure enough, when I measure the proportion of 11th graders that the students had in their classes against the ranking that they're given by the model, they are highly correlated. And here's the two steps I skipped just for time. You'll notice I've added previously to the model. There was a good reason for that. I'm just not going into it. And you'll notice I changed the outcome not to be the scale score on the test, but rather the percent correct on the test. And at the end, I'm going to show you why that turned out. Why, in the end, I figured out why that was probably better. It behaved better, sorry, that's why. So here we did a very good job, a pretty good job of measuring the proportion of 11th graders that each of the teachers, 11th grade records each of the teachers had. So then the concept here was once I got that working, I would just separate each analysis by grade. So I just look at 9th grade, 10th grade, and 11th grade. And I hope that now having handled the grade that the students were, that issue, which you have to handle because they're different tests and you really should do them together like that. That then I would be measuring how effective the teacher was with the students. And so that's what the model looks like. And you'll see what I've done there in the first level. The grade of the student is a characteristic of the student. So that's added in place of the intercept. And now what I end up with is 3 separate rankings of the teachers. One to show how they're doing with 9th graders, one to show how they're doing with 10th graders, and one to show how they're doing with 11th graders. I don't have one to show how they're doing with 12th graders because the 12th graders don't take a test. So now this would give us rankings, and so we could right away say, okay, here's my good teachers, here's my bad teachers, and we'd be ready to go. But my goal here was to decide, are these differences in the ranking, are they statistically significant? Have I gotten through the noise, or have I not gotten through the noise? So I wanted to have some assessment of the statistical significance of these differences. And to do that, what I did is I took the mid-range teachers in each ranking, so there were 12 teachers. I took the 8 teachers in the middle in each of those rankings. And I took them out of the model and instead replaced them with a gamma naught intercept. So go ahead. So that's the final model. And of course, I needed the ranking model in order to know which of the mid-range teachers to pull. But what it has is just 4 teachers, just they change, different teachers for different rankings. And it just shows the 4 teachers that were the 2 best and the 2 worst according to that previous model. And now those gammas have a p-value attached to them so that I can make an assessment of whether those are statistically significant. So each of these teachers I can decide, are they statistically different from the mid-range teacher or not? And then here's what the results are. You'll see that they were quite minimal. All but 3 of the teachers, of the 12 teachers, were either they were the mid-range teachers or they were indistinguishable from the mid-range teachers. One teacher was particularly showed good growth with the 10th graders, but not the 9th and 11th. Another teacher showed that she had poor growth with the 10th graders and nothing with the 9th and the 11th. And then the last teacher there showed poor growth with the 9th graders and good growth with the 11th graders. And other than that, there was nothing significant. And that doesn't even get into the other things you might be measuring other than growth that I kind of alluded to earlier. But that's what I was able to do with the data I had and the resources that I had to do. Okay, next one. Now I want to talk about the data. This is not data. Please don't think this is data. This is not data. This is a feature of the test, and it's probably a feature of the test that exists in your state test. If you're not from Texas, and it definitely was true of our vertical scale scores, and it remains to be seen about the star scores. I'm very curious to see. But this is the way our test works. So the scale scores over there, and over here is how many questions you get correct. And there's 3 years on here, but you can see it doesn't matter which year you're on. I mean, it has slightly different correlation, slightly different assignments of numbers, but it's the same. It's perfectly the same. 2100 is what they need to have met the standard. And you'll see that's where the line is the shallowest. That means each question is worth about, this bottom part here, each question is worth 14 to 20 points down in that area. So every time you get another question right, you're 14 to 20 points more on the scale score. And then that little notch up there is the commended, is where the students become commended, we call it. And you'll see that beyond commended, suddenly each question is worth more and more and more. This is the model that's designed to ideally measure having at the standard, and so that's why it does that up there. So the Roche model probably lots of your tests behave like this. But what the effect of that is that the students at the top, students who are commended, when they do a little better or a little worse on their test from year to year, they're making giant numbers, and so they're disproportionately affecting the growth scores for the teachers. Next slide. So there's the data again, and you'll see that in my data, there was not a student who got all questions correct on their test 2 years in a row. There's not a student up there in the corner. But there's a handful of students, really almost just a handful, that did better, got all of them right the second year. And there's another handful of students that got all of them right the first year, but not the second year. So that handful up there all gave their teachers big, giant growth scores, right? And that handful over there all gave their teachers giant decline scores. And of course, it's a small number of students, and you can see it's not going to be distributed necessarily evenly among the teachers. And so it's just creating a huge amount of noise in this process. And it doesn't make any sense whatsoever, because those teachers, those students there, if you'll notice the commended mark is with this blank spot. That's the notch, okay? So all of those students were commended both years. So if you teach a student that's commended one year, the year when you get them, and they're commended the next year, should you get growth? Should you get decline? You probably just did your job right. It probably should be a wash. And you could build a model that handles the data that way. I was unaware of this issue when I did this analysis, so that's why I think that the percent correct behaved better than the scale test. But you talk to any educational researcher and they'll tell you use the scale score because that was designed. Right? This is an issue that I have not yet run into anybody that, when I talk to people that understand this, and yet it needs to be part of the model, and you can see why. And then this last slide here is this, those are actually my children's CAT scores, and my son does really well. And you'll notice that in 8th grade, he got everything right on this test. And so the absurdity of it is that, you know, his 8th grade teacher is a really good teacher, probably because he would experience a little bit of that 11th grade effect we talked about in 8th grade, right? And then his 9th grade teachers were substitute teachers, which of course is not true. But that's what happens, is they found there's big giant changes in the scores up to these levels. Next slide. So these are my takeaway points. You probably can read them. Many of them I've kind of touched upon. You can read them, and if while you're reading them, anyone has a pressing question, I'd be happy to try to answer it.
I have a question.
Yeah.
This goes to New York City for the Road Commission talk this way. In New York City, they're interested in the percent that pass the different exams, and of course there's a ceiling effect. Because in some schools, almost all the kids pass, and apparently this is such advanced math that no one has figured out that if you got 98% pass, the next teacher can't look any better, really. It'll probably look worse.
Right. So in every one of these models, you need to think about edge effect. And I don't know how much it matters at the bottom. It might be that it averages out better in the bottom. It's the small number of students that really was the issue there. But there's edge effects at the bottom too, because there's a guessing threshold, right? And you got students that are doing better and worse along that guessing threshold. And again, those jumps are meaningless. And so you could work that issue into your model, and it never even occurred to me until I was really working with the actual test data to do that, and yet it seems like it's an obvious thing that you should manage the edge effects in your test data, and every test has edge data of some sort. Thank you. Oh, yes.
I didn't want to ask a question.
I'm sorry.
Can you speak to the idea that if you're putting a linear regression to a scatter of data, necessarily half the data are going to show lack of growth and the other half are going to show growth because the line's got to go through the middle. And it doesn't matter what the actual gains are in terms of the interest.
Yeah, so, and this is the way I do the research, is because the way it's written in No Child Left Behind, in Race to the Top, which is the national legislation, right? So there's the national legislation, and then there's the state legislation, and then there's what the school districts say they're going to do. This all rolls down, and everybody has the rules, and this is the trendy thing to do right now. It's everywhere. But the way it's written in in Race to the Top is you define what 1 year of growth is. And so an effective teacher gets more than 1 year of growth out of their students, and not effective teacher doesn't. This is the way they define it. But I didn't know how to decide what 1 year of growth was, right? So I didn't do my model that way. I just started asking the research question: are the differences that you can show, are they statistically significant? But I didn't know how to decide what's 1 year of growth. So it's written in a way that makes more sense in that sense. But then how do you define what's 1 year of growth? And then once you do, of course, it's the same problem that we have everywhere, which is we have such disproportionate populations in our schools. Once you make a definition, you kind of do some schools But it's written like that, which seems to make a lot of sense. These things make so much sense to policymakers and the legislators, and then they get put into law, and then the schools naturally hire people to do it, and their job is to do it, not to find out whether it can be done. And so, that's my big perspective here. Somebody should be just doing this to see, can it be done, and what are the issues, and what things have to be handled, and so on.
Okay.